Well, yeah, thanks a lot, Natnil, and yeah, this is exciting. I mean, I know we've been talking about actually an AI program in Addis Ababa since might have been 2014 or 15 or something.
Yeah,
And anyway, quite
true.
quite some time ago. A lot of things have happened in the AI field since then, right? I mean, we've had the whole rise of transformer networks. Natural language processing has been revolutionized. So, on the other hand, I think the AI field is still has more future ahead of it than past behind it, right? So I mean, a lot of exciting things are happened every year, but I mean, even more things are still to come. So I mean, I think it remains like each year is the best time there's ever been to be doing AI, right? Like now,
Yeah,
this year is better than last year. Next year will be even better than this year. So it's an incredible time to be in the AI field. And I wanna talk a little bit about some work in the AI field that I've been involved in. Some of which has actually been done by the guys in Addis at ICOG Labs, along with the other folks within SingularityNET, the blockchain based AI project I'm leading now. And what I want to talk about today is work at the intersection of what I call AGI, artificial general intelligence, with narrow AI, which is AI applied in highly specific areas, right? So, as most of you probably know already, I mean, when AI field was founded, which was, the name AI was invented, I guess, mid 1950s, and the concepts of AI were around before that. You could go back to Norbert Wiener's book Cybernetics in the 1930s, even. I mean, back then, when people thought about AI, they were thinking about making machines that could think in the same way as people, with the same sort of imagination, generality, personality as people. And they were also thinking about machines doing like useful things to, rid people of repetitive work and come up with new insights. But they didn't really distinguish between those two things, right? And then as the AI field got more and more serious after the invention of digital computers, people found it was possible to make AI programs that do specific useful things in a way that had not much to do with how the human brain and mind do it, and also was really, really narrowly specialized. Like each computer program was only good at doing one kind of thing. So you could make a chess playing program that didn't know what a chessboard is, right? And certainly didn't know what warfare or cooperation is, and it couldn't play checkers or tic tac toe, right? But it could play chess really, really well. And you could write a program that could, not say drive a car on the highway, but couldn't drive the car whatsoever on city streets. So you could make AI programs that do really, really specific things well, and can't generalize beyond what they were trained or programmed to do, can't use imagination to leap to different kinds of tasks and so forth in the way that a person can. So the AI field became what I would now call narrow AI, meaning AI programs that do highly specific things, right? And this, at some points in the history of AI, like the 70s and 80s, took the form of like narrow AI expert systems, programs that were just hardwired with specific rules for how to do certain things. Now, more narrow AI systems are machine learning systems where one gets a data set and one trains, say, a neural net or other sort of machine learning model on that data set. So, say if you want an AI to recognize faces. You give it a whole bunch of pictures of people's faces with the names of the people attached, and then use that to train the AI. So machine learning in many ways is more powerful than rule-based expert systems of the past. Still, most machine learning systems today are very narrow systems in the sense that they're closely tied to their training data, and they solve the particular problem that their training data encapsulates, right? So if you want to train an AI for face recognition, you give it a bunch of pictures of faces, it's good at face recognition. That doesn't directly help the AI recognize anything besides faces, right? And so if you want to train a narrow AI to drive trucks, you would give it a bunch of data captured from trucks as people drove them, but that system wouldn't then be able to drive, say, a car or a motorcycle, a tank or whatever, right? Whereas, the way we work is a bit different. Like if I learn to drive a truck, that gives me a bit of a head start in learning to drive a tank or a car afterwards, even if it doesn't totally let me learn how to do those different things. And if I learn how to play chess, I mean, some of the strategic knowledge I gained will help me play checkers or something else like that, right? So it's amazing what can be done with narrow AI systems and narrow machine learning systems in particular, but yet it's still different than what human beings are doing. And so we have concepts now like transfer learning, like the ability to take what you learned from one kind of training data set or one kind of task and transfer it to others, and say lifelong learning, the ability of an AI to keep learning more and more things over months and years progressively, rather than just learning in a batch during one round of training. I mean, there's reinforcement learning, which is a collection of ways to learn not from a big training data set you're given all at once, but from feedback about what you do. Was this thing I did good or bad? Was that thing I did good or bad? Was that thing I did good or bad? And all these techniques of like lifelong learning, reinforcement learning, transfer learning, these are elements of what I think of as artificial general intelligence, or AGI, which is a term that I introduced like 15 years ago or something. And while narrow AI is taking over the world economy, AGI remains a research project. Like no one yet has demonstrated they know how to build an artificial general intelligence. Although in science fiction, of course, AGI is like what AI means, right? But it's robots that can do stuff like people, or machine that could run the whole country or something, right? But in actual practice in commerce now, AI is narrow AI. And then, there's a not that large number of research groups trying to push toward AGI. So, my own group with the OpenCog project, which is now largely sponsored by SingularityNET Foundation, we're making our own push toward AGI using an approach called OpenCog, which represents knowledge in a weighted labeled hypergraph, and then has many AI algorithms act on that hypergraph, like including neural nets, including logic engine, including evolutionary learning, and the other methods. Now, Google DeepMind and Google Brain have their own AGI teams. Facebook AI research has its own approach to AGI. OpenAI is working on it. So it's just AGI is a serious research pursuit now, but it's still at the level of research, right? And what I want to talk about in the rest of my time today is what I've been referring to sort of oxymoronically as narrow AGI, which sounds kind of silly. How can you be narrow and general at the same time? But I mean, what I mean by the somewhat silly term of narrow AGI is systems that display significant properties of general intelligence, but focused mainly in some particular domain. Like you can have a system that does, say, traffic management or controls a humanoid robot, say, and it shows more and more signs of general intelligence, of imagination, creativity, of generalization beyond its experience and training. But it does that within the context of a specific application area. And this is one way that we might move, from narrow AI toward general intelligence, is by systems that operate in specific areas, and they step by step broaden the generality of intelligence that they can show. I mean, it's not necessarily the only way to get to true general intelligence, right? But it's an interesting way in the sense that it lets you sort of gradually morph commercially interesting and practically relevant AI stuff in the direction of general intelligence. So yeah, I'm gonna try to share my screen now. Hold on a moment. All right, there we go. Yeah, so I'm gonna give at a pretty cursory level, but hopefully enough to give some idea of what's going on. Some applications on Neural-Symbolic, Neural AGI. And what Neural-Symbolic means is these are applications that the AI systems underlying these applications combine neural networks, deep or shallow neural nets, with symbolic reasoning engines. And this is what I think is going to be one of the major directions of AI progress over coming years is putting together neural nets with their ability to recognize patterns in huge data sets, with symbolic reasoning systems with their ability to represent abstraction in an elegant and generalizable way. And then much of my own work with things like the OpenCog AGI system and the SingularityNET framework for combining multiple AI agents in a decentralized way. Much of my work with OpenCog and SingularityNET is exploring different ways to combine multiple different AI algorithms into combined systems. And Neural-Symbolic is one key use case for systems like OpenCog or SingularityNET that can combine multiple AI algorithms into combined systems. So, yeah, this slide sort of reiterates what I've just said. I mean, narrow AGI refers to systems with strong abilities to generalize, transfer, and abstract, but with a focus on a certain application domain. And one approach to full-on human-level AGI is by improving and integrating multiple narrow AGI systems. And there could be many ways to make narrow AGI. One way is a sort of integrative methodology where you take, say, a neural and a symbolic and an evolutionary system, and you have them all work together. And I mean, the theory underlying this is complicated, but the upshot is by combining multiple different AI algorithms and approaches, one can often get more robust generalization than by taking just a single algorithm. One of the core ideas being what I call cognitive synergy, which means like when your neural net gets stuck, maybe this symbolic reasoning engine can help it out. If your logical reasoning engine gets stuck, maybe a neural net or evolutionary algorithm can help it out. So if you have a number of AI algorithms with complementary strengths and weaknesses, you get more coverage of the problem landscape than with just one algorithm. And there's a bunch of math theory and decades of prototyping and experimentation behind this. I mean, it's still not proven definitively as the golden path to AGI, but it's the approach that my team has been working on. So I'm going to talk a bit now about work in visual scene understanding and in visual question answering and other kinds of sort of sensorially grounded language understanding. And then just briefly talk about how you may get from this sort of application to like real AGI, and then some commercial applications like medical robotics and so forth, which are helpful along the way. So yeah, let's talk about visual scene understanding. So there's a lot of different approaches to having an AI really understand what's happening in the scene coming through a camera. I'm going to describe an approach that works by combining neural networks with logical reasoning in OpenCog's atom space. So, as one example, you may have a picture like this, and you could have a question like, what shape is the large metallic object? Now, there's many different approaches here. You could take a purely neural net approach. What we've done is we've used neural nets to recognize different shapes, different objects, different things, and associate them with different positions in an image. And then you store the information of what the neural net recognized at different places in the image in basically a hypergraph database, which is OpenCog's atom space, sort of like a graph database on steroids with more abstraction there. And then you can submit logical queries, of which this is an actual example. You could submit logical queries like this into OpenCog, and then you can get an answer to things like what shape is the large metallic object. And I guess in the olden days when Natnail and I worked together, I guess you were working a bit with some of this OpenCog pattern matcher language and so forth. So, but at that point, we weren't connecting OpenCog with deep neural nets for vision recognition, and we've got that connection working now, which is interesting. So you use OpenCog for sort of the logical reasoning and cognitive part, but then you're using deep neural nets for the perception part, and you're connecting them together, much as the human brain has different sub-assemblies for perception, cognition, action, language, and so forth. So you ask what color is the plane. You have a neural net that recognizes color, a neural net that recognizes planes, and then these are both associated with the same position. So then you can ask the logic engine what color is the plane, and it knows the plane is red, right? So that's interesting for a lot of applications. And one thing we've done with this in connection with Cisco systems was we use this for real-time traffic analytics. So I mean, you're looking at street scenes there, and you're trying to recognize like anomalous behaviors, like jaywalking. There's a guy walking across the street where he shouldn't ought to be, right? So the AI can automatically recognize behaviors that are unusual or that violate some rules that you have by having the symbolic AI system recognize patterns of what's usual in the combination of visual percept. So like cars parked in a row happens everywhere, not interesting. If there was a car parked in the middle of the street, that's be interesting. If there's a guy walking through the middle of the street, slightly more interesting than cars parked in a row. So you can use these neural symbolic systems for pedestrian analytics also. So you have, say, street scene cameras watching people out in the road, and then the AI can automatically recognize rules like, okay, these people, they came into the square together, they hung out together for a while, then they left together. They're probably a family, right? So the symbolic reasoning engine recognized that's probably a family because they were hanging together the whole time they left and entered the scene. The neural net, though, recognized where the people were and recognized the people walking and did the low level perception. So we're looking at relations like who arrived together, who left together, who's standing up, who's waiting for someone. And the AI learns how to build up a relationship like waiting for more basic perceptions. But you need a neural net to do the basic perceptions. Now we're not in this particular application trying to get the neural net to drive the relationship waiting for. You could do that, but we're using a logic engine to automatically learn the relationship waiting for. But the neural net is recognizing that it's like the same guy in this place and in that place, right? So that's neural symbolic reasoning for human relations analysis. So, I mean, you're learning rules like, if people arrived together and they stayed together while they were there, they're probably going to leave together. Doesn't have to be true, but it's true with a certain probability. And the logical inference here is, it's causal and probabilistic. It's not just plain strict predicate logic. But I mean, you can do one-shot predictions here. Like you could see a situation that was never seen before, say two families coming in together and then hanging out together or something. You can make a one-shot prediction on what may happen out of that one situation, which is harder to do with a purely neural system, predicting about a new kind of situation that you don't have a lot of training examples for. Logic is a bit better at extrapolating sort of from a unique situation. And then, when you have a new video, something like a child there by themselves or something, you want to be able to transfer knowledge to, there's a child there. Children are usually with a family. So the first time we see a child by themselves, even though that wasn't there in the previous videos we looked at, we want to be able to extrapolate and figure out, well, that child probably has a family somewhere. And if they don't, that's a weird thing that we should take account of, right? So that's one example where, it's not AGI yet, but it's also a little more general than, say, just face recognition or something, because you're abstracting general purpose rules from visual scenes. Now, I'm going to talk a bit now about going from text to logic by a couple of neural models, a related but different application. So here you want to basically take natural language and not just generate natural language in response, but you want to generate like structured rules out of the natural language. And one simple use case here is controlling a home automation system, right? Like say you might want to tell your smart coffee pot to make you a pot of coffee when you wake up in the morning, like unless it's on the weekend or something, or unless you already have some iced coffee in the refrigerator, right? So you want to be able to tell it that rule about when to make your coffee in the morning in English, and then have it turn it into like control schematics for controlling your coffee pot and processing the data coming out from the camera in your refrigerator, right? So that's going from text to logic. And we do that using a combination of logical rules represented in OpenCog's atom space, which is a logical language called Atomese, and a bunch of different neural models, seek-to-seek and transformer neural models. And there's a lot of complexity here that I'm not going to try to convey in such a short talk. I mean, if you're not familiar with these neural models, I mean, you'll have to look them up and read about what they are. But I'm trying to just convey the type of thing you can do by combining multiple kinds of neural models with logic systems, right? So we're taking a language model, which is something like everyone's heard of GPT-3 now. Like this is a general model of language, but I mean GPT-3 wasn't the first one. You had Google's BERT model, you had GPT, then you had there's a whole bunch of other neural models that basically learn to predict natural language. So you give them some text and they'll predict what text comes next, right? So you want to take a big language model like that, and then we're building on top of that another neural model called the seek-to-seek model, which is mapping language into logic. So you don't just train a neural model to map language into logic. You take a big language model like a GPT or BERT type language model that's just trained on a huge amount of text to predict what comes next in a series of words. You take a huge language model and then you condition it based on a seek-to-seek model, which is trained to take word sequences into logic expressions. Then once you have those logic expressions, then you can do reasoning on them in OpenCog atom space and atomies logic system. So it's a couple different neural nets that's then chained together to feed into a logic system. And some really simple examples here, like you feed a bunch of pictures of blobs like this and ask questions like, say, how many blocks are tiny blue objects or big purple metallic objects, right? Or I say, is there any mirror in the photo that is not round? So you have questions like that involve a little bit of logic reasoning combined with visual perception, and we're able to answer those by chaining together these different neural networks with a logic system for question answering. Do you see dressers or chairs in the photo? Which kind of device is presented in the picture? And I mean, what our system does here, it takes the natural language and it automatically turns that into a structured logical query, which can then be run in a logic system like OpenCog's atom space. So then you need a logic system coupled with a neural net to be able to resolve that logical query. But that sort of comes back to the kind of thing we were doing in the traffic and pedestrian analysis examples, right? Because in the traffic and pedestrian analysis examples, we were using neural nets and logic to recognize patterns. Here, we're using neural nets to translate English queries into structured queries, which then, to resolve them, needs that same kind of neural-symbolic thing we were doing in the pedestrian and traffic analytics case. So if you want to deal with home automation, I mean, if you had a home where all your appliances and electrical devices were connected to a common computer control system, I mean, you want to give commands like, say, turn off the light bulb in the cabinet. What's the temperature in the kitchen? Increase the brightness of the lamp in the hallway, in the corridor, right? So they're not that complicated. They're simple logic expressions, but actually, like an Alexa or a Google Home does very badly at these things unless you word them in a very, very precise way. And this sort of system can take a more general statement, resolve it logically to its components, and then turn those into like perceptions and actions to control the home automation system. So I think this sort of thing will be needed to make home automation practical. And we're actually now working with a group in Hong Kong that makes new luxury apartments to build in this sort of AI system, like wire it into the apartment along with a whole bunch of smart appliances and so forth. So there's a lot of subtlety here when you really fall down. So you turn the light on. Well, if the light's already turned on, you don't really need to tell it to turn on, right? And in some houses, you need to turn the electrical socket on before you can turn the light on. In others, you don't. If you just say, like, make it brighter in the living room, there could be a couple approaches, right? If it's daytime, you might want to just open the curtains. On the other hand, if there's someone like naked in the room, then you don't want to open the curtains. You want to turn the light on instead, right? So if you could give a command like it's too dark in here, let the system figure out how to make it not be too dark in here, then you have more avenue for logical reasoning. And then you need the reasoning to incorporate context and background knowledge and so forth. So the home automation is a very practical commercial use case that we're actually working on now, mostly in the context of smart kitchens with a Hong Kong customer we're working with. But the same basic approach is needed to solve, say, math word problems, right? Like, say, look at this last one, a math Olympiad question. A group of girls stands in a circle. Emily is the fifth on the left from Mary and the sixth on the right from Emily. How many girls are in the group, right? Like, a person will solve this by drawing a diagram. GPT-3 can't solve it, right? And there's a recent paper showing that neural net systems that solve math word problems are actually not doing it in a very smart way. They're just relying on very shallow syntactic cues in the problem. So if you give a problem that's kind of phrased in a different way than any of the problems in the training data set, it's going to screw up, right? Whereas a neural-symbolic system could solve a math word problem even if it's in a different style than the ones in the training data set, because it's figuring it out like based on actually understanding what's going on, right? But we're still, this is still a research problem. We don't yet have a neural-symbolic system that can win the math Olympiad, right? But I think it's a very interesting direction to work on. So I've gone over some practical applications of systems that are neural-symbolic and make sort of partial fragmentary progress toward AGI in specific domains. So we're working on these from a commercial standpoint. At the same time, we're designing a framework we call True AGI, which is built on the open source OpenCog system, and in particular on a new version of OpenCog called OpenCog Hyperon. And this is trying to work further toward being a real, like, full-on AGI system, in which then multiple narrow AGI pursuits could be done at once. So this is a very rough high-level architecture here. So you look at the far right, you have an atom space, which is like a weighted labeled hypergraph. It's a big graph knowledge base, and you're recognizing symbolic patterns in there. You're also embedding the atom space into vectors using a neural network. Then you may have a local cache of the atom space on specific machines that you're working on. You have some AI that allocates attention, like figures out which parts of this big atom space graph are worth paying attention to. We actually have our own programming language called Atomese, which is like a probabilistic logic language for manipulating the graph database. And then you have sort of sub-languages in this language for neural nets, for probabilistic logic, for evolutionary program learning, and so forth. So you're getting all these different kinds of AI algorithms to work together on this common distributed graph knowledge base. And it's a different approach than, say, Google and Facebook are taking. They're taking more a pure neural net approach, whereas we're integrating neural nets with logic, evolutionary program learning, and so on. On the other hand, they're also, in a way, taking a complex multi-network approach, because they're not trying to get like one neural net to do AGI. They're saying, let's connect one neural net that does visual perception, one neural net that does reinforcement, one neural net that does long-term memory, and connect all those together. So there's also a heterogeneous cognitive architecture. It's just all the boxes in their diagram are different neural nets. Whereas in our approach, some boxes are neural nets, some are logic, some are other sorts of things, right? So then, I won't go into too much depth on this here, but we're designing a new programming language called Atomese, which is designed to make it easier to connect all these different AI algorithms. So, lastly, I want to briefly mention a practical application. We're using the OpenCog framework together with a number of deep neural nets for vision and language in this now. And then we're going to upgrade this to the new version of OpenCog Hyperon in a year or so, once that gets more mature. So this it's a partnership of Hanson Robotics, which is the company that built the robot Sophia, whose software was partly built at ICOG Labs in Addis, and which we brought to meet to Abi like a few years ago, right? So Hanson Robotics, who built Sophia, and then SingularityNET, the company I'm running now, which is sponsoring OpenCog development, and also building a decentralized blockchain-based AI platform that lets many AI agents like coordinate and cooperate together without any central controller. So SingularityNET and Hanson Robotics partnered to create a company called Awakening Health, which is making robots that look like people and act as much as possible like people, which are aimed at elder care facilities, like senior living facilities, old folks' homes, hospitals, and so forth. So these are like supposed to be robot nursing assistants. So this is an artist rendering of what the robot looks like. The first Grace we actually have right now Grace is a disembodied head. Like we have a head of the Grace robot. We're connecting her in the next few weeks to a body with a wheeled base, and it's basically Sophia's little sister. So this is but specialized for the medical domain and running exclusively on SingularityNet's OpenCog plus Neural-Net software, right? And so the architecture here, you have audio sensors, video sensors, medical sensors, using neural nets for audio and video processing. Then you're feeding this into a complex cognitive architecture based on OpenCog system that includes all sorts of reasoning, learning, and motivation and so forth. And then once the OpenCog system decides what the robot should do, you have neural nets for going to speech. You have neural nets for controlling the animation and movement on the robot's face. And you have neural nets that control the movement of the robot around in the hospital. So this I think is a kind of system that can really serve as a powerful narrow AGI system, in the sense that, it's a nursing assistant. It doesn't need to do everything a person can do. It needs to operate in a hospital and be able to help patients. So in that sense, it's narrow. On the other hand, you can get a whole lot of crazy situations in a hospital or old folks' home. Each patient is their own story. So the system also needs to generalize and transfer knowledge from its prior situations to the new situation, right? And so this I think should be a very interesting playground for our neural-symbolic narrow AGI work. The hardware for that is being done in Hong Kong with some assemblies made in mainland China in Hanson Robotics, but the software is being done partly in Addis at ICOG Labs, a lot of it in St. Petersburg, Russia, some of it in Bangalore and Brazil. So SingularityNet's AI team is sort of all over the place. The beauty of software is all you need is like a laptop, electricity, and an internet connection, right? And even Ethiopia mostly has those things. We had some internet connection problems last year, but not 90% anyway. And so this has been really interesting. I think it's going to get much more interesting in the next year. Like we're rolling out the first 4 of these Grace robots in April, and we're going to start like putting them into old folks' homes on a prototype basis. And I mean, the more the robots go out there and help people, the more they learn. And with the ability to generalize and transfer learn, then the more they learn, the more different situations they'll be able to deal with, then the better product they'll be. You get some virtuous cycles going there. But I mean, in conclusion, though, I want to stress, well, robots are super cool, and they're sort of the science fiction vision of what AI is supposed to be. Like I had a bunch of slides in this deck that I didn't give, which were on actually genomics and trying to understand the causes of human aging and understand which breast cancer medicines work for which patients and so forth. So I mean, something like that, like understanding how the body works and then which medicines you should give to which people based on their own physiological makeup. I mean, this is just as good a narrow AGI application as humanoid robotics. And I've done a lot of work on that, and we did a lot on that in ICOG Labs also. But I think it's not quite as easy to explain to people on the surface level as robots, right? So the robots are cool. They're great for showing off. They're also arguably the best way to get sort of the everyday aspects of human culture and ethics and personality into the robot. But actually, AI is pervading every aspect of industry and human pursuit. I mean, you got AI in agriculture. We did some things with, say, AI for diagnosing crop disease, for pictures of leaves of plants and so forth. Some interns in Addis Ababa University did that actually for diagnosing disease in coffee plants from photos of the leaves. Then we did that in Sichuan province in China for different kinds of plants. So you have AI applied to agriculture. I mean, we're actually, David Hansen is doing a NFT, non-fungible token drop tomorrow of some AI generated artworks, which is being sold by a major art gallery. So you have creative painting and creative arts. So I'm in the everything you name it, like AI can do it now. And the challenge is really broadening the AI's learning to move from very narrow AI applications toward more and more general intelligence. And I think for those of you coming into the AI field now, like you're coming in in a way an insanely lucky time. Like I started with AI in the 1980s when the field was quite obscure and computers were so bad it was very hard to get anything to work. Like now you're coming into the field when AI is working really well, and during your careers, you're likely to see the transition from narrow AI to generally intelligent machines that can really think, and then you get to play a part in that, which is pretty fun, right? Like it's like being involved with building factories in the beginning of the Industrial Revolution, or being involved with like quantum mechanics in the 1920s and 30s when it was first being invented. So it is a pretty awesome time to be coming into the field. So yeah, I'm really psyched that you're getting an AI program in Addis. I mean, through ICOG and otherwise, a whole bunch of people in Addis have learned AI anyway. But having a university program for it is even better, and I'm hopeful it's going to grow really fast now that it's finally going.
Sure, sure. Probably it will go. I mean, in a better way if you engage, if ICOG Labs engage more often.
Yeah, I mean, I'm eager to help. I mean, I wanted to like 7 years ago or something, but it took a little while to get the wheels turning. But yeah, I think there's a lot of ways that SingularityNet and the OpenCog community can work together with you guys. And yeah, we're doing a whole bunch in ICOG now with AI, and also the intersection of AI and blockchain, which I didn't talk about here. Like we're sharing an office in Addis between ICOG and IOHK, which is a company behind Cardano blockchain. So
Okay.
we're doing a bunch of things with AI applied to genomics, with robotics and AI for creative arts, but also with like distributed processing power. So like how can you take the processing on everyone's phone and everyone's laptop
Mm.
and network it together in a way that lets you run an AI process collaboratively across like thousands of people's phones and laptops, right? So there's a whole whole lot of different AI applications which are being worked on, like in Bole at this moment, right? I mean, there's as well as in our other offices around the world. So yeah, it should be cool to engage with you guys on all sorts of things.
Thank you, Dr. Ben. Now I will let our students to ask question if there is any.
Yeah, let's have a few questions.
Yeah,
Great.
yeah. We have also invited some of our colleagues in Addis Ababa University. They are here. Um, I think if you have any question, you are welcome to forward. I have only one question actually. The lecture that you have. uh, offered to us is very interesting, especially the integration of the classic machine learning, the neural network-based machine learning with the logic. It's very interesting, and I hope, I'm sure, I think it will yield a better result. But about this project, about the Grace project, is it inspired by the telehealth project a little bit?
Well, it is similar in spirit, yeah. But this telehealth project was that was for home use, right? So that was sort of a talking pill dispenser aimed at chronically ill people who are at home, and it did have an avatar dialogue system, right? So the avatar dialogue system is similar, but being in a hospital or like senior living context is very different from a product perspective, right? Because it's more of a controlled environment, which makes it a bit easier. Like walking around someone's house is quite hard because people's houses can be
Yeah.
quite heterogeneous, right? But yeah, in terms of the dialogue system aspect, it is. But one aspect of that project that you were involved with was we, due to the requirements of that customer, the dialogue system controlling the conversation of the telehealth avatar had to run on a tablet, right? Whereas now what we're going to do is put a bunch of servers in each hospital, which will sort of be like the hive mind for all the different robots in the hospital. And I mean that lets you put like a bunch of GPUs for the neural models and machines with a big CPU and multiple processors for the OpenCog system. So I mean, you need more than the tablet at this point to run a more serious AI system. Although you can do some processing on a tablet or on a robot or something. So yeah, it's definitely similar inspiration. But I mean, you'll find there's not that many radically new ideas in AI. Like most of the stuff people have been trying to do since like 1960s and 70s, and it's just the supporting technologies were too bad. Like the cameras were too bad, or the processors were too bad, or the data sets were too small. So we're seeing a lot of the same core ideas and a lot of applications that were tried over and over and over again.
Mm.
People are trying now, and just the supporting infrastructure is better, so they're finally working, right? Like face recognition. I mean, we were trying that in the 80s and 90s. You could sort of do it, just didn't work as well. Like I think my company, my AI consulting company, I think in 2002 or three, we built a face recognition security system using support vector machines. It worked, but you had to like have just the right lighting on the guy's face, and if they had grown a beard, it wouldn't work or something, right? And now you can overcome those problems. So yeah, that's an open question whether you need some like weird, radically new idea that nobody ever imagined to make the breakthrough to AGI, or whether things we already know about, like neural nets and probabilistic logic engines and graph databases, like whether the things we already know about connected in the right way and run on enough machines are going to be enough, right? And that's yet to be discovered. Obviously, I'm sort of the latter persuasion, where I think we're not that far off from AGI, but it's to be discovered. I mean, if we knew what was going to happen, it'd be a lot less fun.
Yeah. Actually, very related to this one, do you think we can realize AGI within the next like 30, 40 years?
I definitely do. I think the question for me is, can we get there in the next 10 years?
Yes.
Which is the way I look at that is, you know, computer vision between say 2014 and 2017 just went through incredible progress. From like you had AlexNet and these early computer vision competitions, and then within a few years after that, computer vision was just working for so many practical applications, right? Natural language processing, from when you had BERT, like Google's first transformer neural net model, in 2018 until now, it's just been incredible progress with NLP. Not that every problem is solved, but we went from very crude systems to really very advanced systems, right? So I think we're going to see a period of a few years of intensive progress like that for AGI, right? And that's going to get us from AGI being very primitive and dodgy and researchy to AGI like being a real technology that is displaying general intelligence in real applications. And once we have like a few years of this like burst of incredible progress in AGI, then you're going to see literally trillions of dollars of R&D going into AGI, and things are, like you're seeing with computer vision and NLP now, and things are going to start advancing incredibly fast. The question is, when will that few years of intensive AGI progress come? So that, and nobody knows that. I mean, from a sort of egocentric view, like we're working on OpenCog Hyperon, the new version of OpenCog that'll probably launch in a couple years. So maybe that will trigger the explosion of progress, right? But if not our system, it's going to be somebody's fairly soon, I think. I mean, maybe something invented by someone in this class. Who knows?
It's good to be optimist.
Well, I mean, the optimists definitely have more fun, right? So,
Yeah, sure. Okay. Thank you, Dr. Ben.
Yeah. Thanks, everyone. And I guess folks will have more questions as the
I think
semester proceeds, right?
Tasfai has raised his hand, so he can
All
ask.
right, sure. Let's have a question.
Yes, sir. It's a great pleasure to attend your session. And my question is that what are the main challenges in this sector in AGI implementation and realization when it comes to like is it the software part or the hardware that deals with sensors and some other electromechanical stuffs? Which one is the biggest challenge to realize the AGI? And the second one is that uh, when we deal with human nature, most of our our knowledge are tacit knowledge. They are not in the form of written or uh, articulated situations. So how an AGI how is it possible to incorporate these kinds of tacit knowledge when you design or in the future of AGI, how are we going to cope up with this kind of knowledge challenge or information
Well, yeah,
challenge?
no, those are both good questions. So for the second question, I mean, I think our tacit knowledge comes from two places, right? It comes from evolution, like what's basically wired into our bodies from our evolutionary history, and then it comes from what we learned during experience. So learning through experience is something AIs are going to have to do, and this is part of why I like, use cases like social robots that are out there in the everyday world. Because, if an AI is in a hospital room watching doctors come in and out, watching patients do things, hearing people talk in the background, I mean, it's going to get tacit knowledge from experience just as little kids do. Like little babies don't know much, and they get it by recognizing patterns in what they see. The inductive biases that we get from evolution that are in our brains at birth, this is a more interesting challenge, right? Because you could argue that the structure of the brain embodies some intuitions about how the world works. The AI doesn't necessarily have all of those. On the other hand, the AI has like all of the internet and all the videos on the internet to to recognize patterns in, which is an asset that no human baby or adult has, right? So in that case, the AI just has different strengths and weaknesses than people, and it's an experimental project to see like how can you overcome the lack of evolutionary inductive biases for learning with like the surfeit of diverse data that the AI has at its disposal, and we got to try and see, right? Then the first question, I think sensors are not the big problem now. The sensors robots have are better in some ways, worse in some ways than the ones the human body has, but they're good enough, right? And I think the hardware we have, in my best guesstimate, is good enough for human level AGI, but like probably my laptop isn't, right? Like you probably need a big server farm, which is expensive. So I think while the software is the main challenge, of course, if everyone's laptop had the power that Google now has, like wrapped up in a laptop instead of a huge server farm, then every programmer could run faster and more experiments with their software, right? So I think while figuring out exactly how to configure and set up the AI algorithms is the main bottleneck, there's no doubt as hardware advances, the experimentation you need to do to create the software will go faster. So right now, say working with transformer neural networks or with OpenCog's reasoning engine, you're often like setting some parameters in an algorithm, then let it run for a few days, right? So that's a slow process. If that experiment that now takes a few days took 5 seconds, right? Then you could explore a hypothesis much faster. So yeah, I think as the hardware gets faster, then the programmer's learning process and experimenting with things will get faster, and folks who don't have huge amounts of money for computing machinery will be able to make more and more progress, right? Because that's one of the things we're looking at with SingularityNET is like how can you use like decentralized processing to let people who don't have a huge server farm do serious AI experiments, because like to train say a GPT-3 type model takes millions of dollars of compute power, right? So then in a way, if you don't have millions of dollars for compute power, then you're constrained in what you can do. You can publish a paper, but you can't experiment with the algorithm in your paper on a huge data set, right? So that's it could end up being an advantage for those without millions of dollars for compute power, because you're forced to build algorithms that can do more with less. But there's also a limit to that, right? At some point, you're working with too little resources, and you just can't do the research properly.
Thank you so much. Windows and Tesfaye, maybe you have a question, I guess.
Yeah, I have a couple of questions. It's a great pleasure to talk to you, Doctor. And my question is, what is the motivation behind AGI? That means, let's say we develop this super agent. So what's the future holds for humans? And my second question is, what's the path to become AGI programmer?
Yeah, so what the future holds for humans, nobody knows, right? What's the motivation for AGI? I'm tempted to say nobody knows either, because very few humans truly know their own motivations, even in simple aspects of life, let alone building AGI. But I think of course, people want to build AGI because it's really cool and it's sort of an amazing technical challenge. But I think it's also the case that, you know, a machine that was much smarter than humans and well disposed toward humans could, I mean, it could solve material scarcity, right? You could make an AGI scientist and engineer smarter than any human could figure out how to make like a nano 3D printer that could print anyone any material object they want. It could figure out how to cure all human diseases, right? So I mean, clearly, there's essentially no practical problems humanity faces that couldn't be solved by a benevolent machine with an IQ 100 times that of any human. So I mean, the practical upside is pretty clear. So I think that, combined with the ability to make money from smarter and smarter AI systems, combined with the pure intellectual challenge of it, is enough to motivate people to make AGI. And then you have competition, right? Like if US decide to stop making AGI, they know China and Russia aren't stopping, and India isn't stopping. So you got an arms race dynamic there too. So I think you know, the question by now isn't will humanity push to make AGI? The question is, will we be able to push the AGI to be beneficial rather than serving some narrow group's particular aims, like maximizing the military might of some country, or a superhuman AI mind whose only goal is to maximize shareholder value of a certain corporation, right? Like the battle is for the soul of the AGI, not as to whether AGI is going to get worked on or not. So, and I forgot the second question already. But what was the second question?
The second question is, what's the path to become a?
What's the path?
Yeah.
I mean, you know, building AGI needs a lot of different things, certainly, but I'd say the hardest thing for me to find, as someone who runs an AGI or a software project, the hardest thing for me to find personally when hiring is people who are really, really good software engineers and also understand the theory and concepts of AGI. Like finding those two things in one person's brain is very rare and very difficult. But you don't need to have that to contribute. Like I'm not a really good software engineer. I used to be okay, but I've degenerated, right? And we have through too many years in research and management, and I mean, and we have others on our team who are amazing software engineers and don't get the all the AGI theory. So you certainly, you don't need to have that combination to contribute. But if you do, you can have a central role in any AGI project, right? Because finding people who are masterful in engineering and understand all the theory and concepts is super hard. The other thing I'd say is there's a sort of cross-disciplinary discipline called cognitive science, which emerged in the 80s. And cognitive science sort of is a combination of AI, psychology, computer science, linguistics, philosophy, engineering, and sort of how do you put all these together to grapple with the task of creating thinking machines. And I think approaching AI from a cognitive science view rather than just an algorithms and data view is important. Not necessarily if you want to do applied machine learning, but it's important if you want to work toward AGI rather than solely narrow AI applications.
Thank you. Yared, you can ask. I think Yared has a mic issue. I think
Yeah, connection problem perhaps.
Okay. Okay, actually they have forwarded a couple of questions. Those questions were good. I think the answers were also good. Thank you so much, Ben. I hope we will see you again on another lecture session in the near future.
Absolutely. I'm eager to help out, and we can probably pull in some other folks from the OpenCog SingularityNet community as things progress. So yeah. Thanks everyone for listening, and until the next time, guys.
Thank you so much. See you.
Thanks a lot. Thanks. Thank you.